is Professor Umeda, and he will talk on low energy spectral and scattering theory for relativistic Schrödinger operators.
Thank you, Mr. Cohen.
Can you hear me? Okay. So first, I'd like to thank the organizers for inviting me to this beautiful place and for giving me an opportunity to talk in this nice workshop. And I'm going to talk about low energy spectral and scattering theory for relativistic Schrödinger operators. So I'm going to put special emphasis at zero energy and spectrum near the zero energy. And so the operator I'm going to talk about is this operator. By H I mean this operator. Some people call this pseudo-relativistic operator. Others call semi-relativistic operator. But we call this operator relativistic Schrödinger operator because if you replace this part with minus Laplacian, then you get the Schrödinger operator. This is why we call this operator relativistic Schrödinger operator. And this part is the relativistic kinetic energy for massless particle. And this part is the potential. And since I'm going to, so the first half of my talk is about spectral property, and second half is about scattering theory. And scattering theory always needs a pair of operators. And so the other operator is this one, it's a relativistic kinetic energy operator. And throughout my talk, I assume that V of x is a really valued function satisfying this inequality. And here bracket x means here, okay? And I assume that sigma is greater than 1. And later, I need a greater sigma, but at this moment, this is sufficient. Under this assumption, it is easy to see that H and H naught are both self-adjoint operators in this Hilbert space. By this L2, I mean the L2 space over R3. And their domains are given by the Source space of order 1. And it's easy to see that the spectrum of H naught consists of this interval 0 infinity. And since V is a relatively compact perturbation of H naught, so we see that the essential spectrum of H is given by this interval. Okay. So I'm going to give you a notation. So by this notation, I mean the multiplication operator by the bracket x, and by this notation I mean the pseudo-differential operator defined by this, and here capital D means minus I times nabla, and by L2S I mean the weighted L2 space, and here the weight S is always appear as a subscript, and by this notation I mean the weighted Sobolev space. And here, the order of Sobolev space appears always in superscript. And so this is the Sobolev space of order T. So these are the function space which I'm going to, which appears in my later part of talk. So let me first, we have to establish a limiting absorption principle, and actually this was already known by the work by Matania and his former student Nemirovsky, and this is part of what they showed. And first they showed that this means point spectrum of H, the set of eigenvalues of H. And so this means the embedded eigenvalues of H. And this set is discrete if it exists. It may not exist, but if it exists, it is a discrete set. And this set can only accumulate at zero energy or plus infinity. And this is the limiting absorption principle for the operator H. So for any s greater than 1/2, and for any lambda belonging to this set, they show the existence of the boundary values of the resolvent of H. Here, R of Z denotes the resolvent of H. And they took this operator topology. So this means the set of all bounded operators from L to S to H1 minus S. Here, it is important that here S is positive, and here you have minus S as a weight. And what is nice is that they show that these boundary values of the resolvent are locally held are continuous. In particular, it follows that the spectrum of these spectrums are absolutely continuous. So this is the conclusion of what they said. So this is a general picture of the spectrum of H. So here we may have some eigenvalues with finite multiplicity. So sigma d of H denotes the set of eigenvalues with finite multiplicity. And here this is zero energy. This is the threshold energy. And from zero, we have a continuous spectrum. And there might be some embedded eigenvalues. But they can only accumulate at zero or infinity. This is a general picture of the spectrum of H.
Are there examples of embedded eigenvalues for short-range potentials? Or is this just a theoretical possibility?
Just theoretical. So we haven't been unsuccessful to construct such a potential.
I see. Okay, thank you.
So as I said, I am going to put special emphasis at zero energy. And so what we can say is that it is very rare that zero is a eigenvalues of H. To state this in a mathematical rigorous sense, we need a class of potential. And in this case, this space L3 is convenient because if V belongs to L3 space, then V is relatively bounded with respect to H naught. So we can take the operator sum of H naught and V. So I would like to emphasize the dependence of potential V's. So at this moment, I would like to use this notation HV. And what we can say is that this set of potential V such that 0 is not an eigenvalue of HV, this set contains an open and dense subset of L3. So this is my assumption of potential, and we assume that sigma is greater than 1. So V belongs to this class. Okay. And so this theorem means that this set is very big because it is contains an open and dense subset of L3. So this set is very big. In other words, the complement of this set is very small. So in that sense, it is rare that 0 is an eigenvalue of H. This is a rare phenomenon. And the strategy to prove this theorem is based on idea by a paper by Alex Balinsky and Des Evans. So key ingredient is just the same as theirs. So one of the key ingredients is this inequality. And so we sandwich the potential by this Rees potential. Then it becomes an L2 bounded operator in L2, and this means the set of bounded operators in L2. And it is estimated by constant times L3 norms of V. And to prove this inequality, we just use the subleft inequality. And another ingredient is this fact. This sandwich operator is compact in L2. By this notation, I mean the set of compact operators in L2. So these two things are very useful to prove this fact. Okay. So anyway, it is generic that 0 is not an eigenvalue of H. This is generic. So now I would like to concentrate on the zero energy resonance. But what is zero energy resonance? So F is said to be a zero energy resonance of H if and only if F belongs to a space slightly bigger than L2. Just slightly, this is very important. But F does not belong to L2, but still it satisfies this eigenvalue equation. But so this is, F is in a sense an eigenfunction, but it does not belong to L2. So it is not an eigenfunction in its original sense. And what we can say about zero energy resonance is this theorem. So here I need greater sigma. So I require sigma greater than 3/2. And if F belongs to L2 minus S for some S belonging to this interval, so since I assume that sigma is greater than 3/2, so sigma minus 3/2 is positive. And so, and S is always less than 5/2. So this means this space is slightly bigger than L2. Still, F satisfies this equation in distribution, then F has to belong to the domain of H. This means that zero energy F is a zero energy eigenfunction. So this F cannot be a zero energy resonance. Okay? And some people complain about this definition of zero energy resonance. So for such people, we prove this theorem. And so here I assume that F behaves like this at infinity. And so here again, we need further much bigger sigma. So here I assume that sigma is greater than 2. And I assume F belongs to L2 local and satisfies this equation and behaves like this at infinity. And C1, C2 are essentially bounded function on the unit sphere, S2. And since x to the minus 1 does not belong to L2, so this is a candidate of zero energy resonance. Then again, we can show that this F belongs to the domain of H. So with these two theorems, I can say that zero energy resonances do not exist. Okay? So zero energy resonances do not exist. And this fact will play important role when I will speak about the low energy asymptotics of the scattering matrix at the end of my talk. So please remember this fact. So now I would like to concentrate on the point spectrum in the vicinity of zero energy. Not only zero energy, I'm going to think of energy in the vicinity of zero energy in the positive half axis. So here I need further bigger sigma. So I suppose sigma is bigger than 5/2. And if zero does not belong to the point of spectrum, or in other words, there is not an eigenvalue of H, then we can find a positive number such that this interval does not have any intersection with the point spectrum of H. So in other words, if the embedded eigenvalues accumulate at 0, then the accumulation point 0 has to be an eigenvalue of H. This is, to me, this is surprising because the accumulation point has nothing to do with eigenvalues. But this theorem says that the accumulation point has to be an eigenvalue. So this is surprising, I believe. And so the proof of this theorem, so key ingredient is introducing this operator. So this is actually a Riesz potential for the square root of minus Laplacian. So actually the resultant kernel of H naught minus 1. So what we showed is that for any s greater than 1 and for any lambda and any positive lambda, the boundary values of the resolvent of H naught here, R naught of Z denote the resolvent of H naught. They converge, they belong to the compact set from L2S to L2 minus. And what is nice is that these boundary values converges to this operator. And so as a result, this operator, G naught, is also a compact operator. And why we can show this is that we computed the resolvent kernel of H naught explicitly. And looking at the kernel of the resolvent kernel, we can also get the explicit formula for the boundary values of R naught plus of lambda, and then we can prove these two facts. So, of course, it is better to guarantee the non-existence of embedded eigenvalues. For that purpose, we need a strong assumption on V. And so, by this notation, I mean the set of functions which is bounded together with its derivatives up to second order. So this is the definition of this function space. And if V belongs to this space and satisfies these three assumptions, then we can show that H is purely absolutely continuous on this interval. But the important assumption is here 3. So here C1 and C2 are both non-negative, and the sum is less than 1. And it satisfies, it must satisfy this inequality. This means that this potential V is very small. And then we can show this fact. And in particular, the non-existence of embedded eigenvalues follows. So this is so far is the first part of my talk. And so I'm going to talk about the scattering theory. Oh, no, I'm sorry. So I have to say something about the proof of this theorem. So to prove this theorem, we use a variant of method of a weakly conjugate operator. So there is a abstract theorem, and we just applied it. And then we get this result. And in particular, we can show the non-existence of embedded eigenvalues. So now I'm going to talk about wave scattering theory. And the basic object scattering theory is the wave operators. And so in some occasions, I want to emphasize the dependence of the pair H and H naught. So in such case, I use this notation. And these wave operators are defined by this strong limit. So this is a quotient of two unitary propagators. And so each operator is unitary. And so as a result, wave operators are isometric in L2. And it is known that these wave operators are asymptotically complete. That means the range of these two operators are the same, and which is given by the orthogonal complement of the subspace of H spanned by all the eigenfunctions of H. This is the meaning of the asymptotic completeness. And since we have this asymptotic completeness, if we introduce a scattering operator by this formula, then it is a unitary operator in L2. So let me give you a brief review of the scattering operator. So many of you are familiar with the definition of notion of scattering operators. So I would like to go quickly. Anyway, so scattering operator describes scattering, of course. And so since this handwritten figure is ugly, so let me go quick. Okay. And then I would like to introduce the direct integral, which actually gives the definition of scattering matrix. So scattering operator is unitarily equivalent to this direct integral. By this notation, I mean a unitary equivalence, and which unitary transformation gives this equivalence. So to tell you that, I would like to introduce a transformation F naught from L2 to L2 R plus d lambda little h. This little h is the L2 space over S2. And so to define this transformation, I first take here this f is a Fourier transform. So first I take the Fourier transform of f, then I regard it as a little h valued function, and then I multiply lambda. Then this is f naught is a unitary operator from L2 to this space, because I have lambda here. So if you take the square, then you have lambda squared here. So this is a unitary operator from L2 to this space. Then it is important that if you sandwich the scattering operator like this, then it becomes a BH. BH means the operator algebra on this Hilbert space. So BH valued multiplication operator. So this is action of this operator. And what is important is that if you take the inner product in this space, then it is equal to this quantity. And here you take the inner product in the little h Hilbert space, and the integral from 0 to infinity. So this is why we adopt this notation. So this is the basic fact about scattering matrices. And we'd like to know what happened if lambda tends to 0. What happened to S of lambda? This is what we'd like to know. And for that purpose, we introduce a duration group, which is defined by this formula. And so since we have this factor e to the 3 tau over 2, this defines a unitary operator, and moreover, it gives a unitary group. And then if you compute this sandwich, then it's just simply a multiplication e to the tau to h naught. And if you sandwich v like this, then it becomes a multiplication by v tau, and v tau is defined by this. And the most importantly, wave operator are transformed in this form. And so this is the wave operator between the pair of h naught plus e to the minus tau v tau and h naught. And what is important here is that okay, so let me go this fast. So if you sandwich the scattering operator, then you get this expression. here S is the same as before. This one. And so if tau tends to minus infinity, this part e to the tau lambda tends to 0. So tau tends to minus infinity means low energy limit. And so for this reason, we are going to take the limit as tau tends to minus infinity. And in that way, we examine the low energy asymptotics of wave operators and scattering operators. But e to the minus tau becomes infinity when tau minus infinity. But the support of v tau shrinks to the origin. So this part becomes something like delta interaction. Okay? And to investigate the low energy asymptotics of the scattering matrix, we need assumption, two assumptions. And unfortunately, both of them are implicit assumptions. But as I said, it is generic that 0 is not an accumulation point of embedded eigenvalue. So generically, this assumption is satisfied. And I need further assumptions. So let P be the projection on G naught. This is defined as the kernel of 1 plus U G naught V. Here, little u means the square root of the potential V, and little v means the square root of the magnitude of V. And so what is important is that product of little u and little v gives the potential v. This is important. And the kernel of 1 plus u, because of this fact, kernel of 1 plus u g naught v is the same as essentially, it is the same as the kernel of H. And so, as I said, this kernel of H is generically the trivial space. And also, the assumption too, whatever it is, it looks complicated, but whatever it is generically verified. And so, this is what I said. Also, if potential V is very small, then both assumptions are verified. And so, this is the low energy asymptotics of wave operators. So here we need bigger sigma. Sigma is assumed to be greater than 3, and these implicit assumptions hold. Then the strong limit of the sandwich wave operator is identity. So as I said, this means a low energy asymptotics of wave operator. And as a corollary, we get this statement. And so generically, scattering operator, here S is a scattering operator. So scattering operator converges to identity operator. So this is an important theorem, and the key ingredient of the proof of this theorem is this expression. So definition of wave operator contains unitary groups of H naught and H, and so it is hard to analyze. But if we apply this stationary expression of wave operators, then we can handle wave operators. As I said, So this is investigating this operator is the same as this sandwich wave operator. So this is why we investigate this operator instead. So we have this stationary expression of wave operators. Here, alpha of z is the resultant of h naught plus e to the minus tau v tau. And we don't like this operator because it is not explicit. And to make this explicit, we use the resultant equation. Here, you see, but this one, R naught of z is the resultant of h naught. And so it can be, it is manageable. Here you see R naught again. U naught, U minus tau is just a dilation. Here V is essentially the square root of potential. And here you have R naught, the resultant of H naught, and U and V, it's okay. And U and dilation R naught. So with this resultant equation, we can control the right-hand side. This is the basic idea how to prove theorem 7. Okay. So then this is our purpose. So if we assume that sigma is greater than 3 and these two implicit assumptions hold, then the low energy limit of the scattering matrix is identity in this space. And again, little h means the Hilbert L2 space over the unit sphere. And to prove this fact, again, we use the stationary expression of scattering matrix, which is given by this expression. And here, this F naught is the same as this one, but here this is a operator. It works this way, but if we regard this this defined a bounded operator in this little h, then we can regard this F naught like this, and since I multiply lambda in front of f, and so as lambda tends to 0, F naught of lambda behaves like this. And so this part tends to 0, and also this part also tends to 0 as lambda tends to go to 0. So these green parts are okay. So the problem comes from here. But using the explicit formula for R naught, we are likely that this part stay bounded as lambda tends to 0. So as a result, S of lambda scattering matrix converges to identity operator in Hilbert space little h. Now I would like to compare the non-relativistic case. So here we replace square root of minus Laplacian with minus Laplacian. And the famous result by Jensen Kato, what they derived is this asymptotic expansion. So their result is much more precise than ours. But this is because the resultant kernel of minus Laplacian is, in a sense, simpler. But in our case, the resultant kernel of square root of minus Laplacian is a complicated function, and so all we can do was this limit is equal to identity. But anyway, what is important here is that at the limit as lambda tends to 0, the limit operator is sigma naught is identity or identity plus rank 1 operator. This difference occurs because the existence of zero resonance. And if there are no resonances, then sigma naught becomes identity. But if there are zero resonances, then sigma naught becomes identity plus rank 1 operator. And so, as you see, there is a difference between relativistic case and the non-relativistic case. So this is a difference. And so finally, a conclusion and further prospect. So low energy behavior of the wave operators and scattering operator is now better understood. But how about high energy behavior? We don't know. So this might be the next project. And also to investigate the embedded eigenvalues, we impose strict assumptions. So it is also a matter to weaken the assumption to investigate embedded eigenvalues. And so that's all. I still have 10 minutes, but it's okay. Thank you.
Okay. So after this Kato-Jensen paper, there were several papers by Jensen himself where he studied dimension 4 and 5, and he proved that in these higher dimensions you don't have the alternative, but you also have only the limit 1.
Yes.
Do I understand correctly that for you, for the square root, the three-dimensional case is like for the non-relativistic case, the 5 and higher case? And so my second question is, do you expect that if you do the same thing here in 1 and 2 dimensions, do you then get the Kato-Jensen alternative between 1 and 1 plus rank 1?
I expect that 1 plus something in 2 dimensions.
In 2 dimensions,
yeah.
I see, okay.
And higher dimension, I don't know.
Okay. No, sure, but then it should be nicer in higher dimensions. Sure, okay. Thank you.
In your model, there was the square root of the Laplacian. Now, suppose you replace the square root by any other, let's say, positive exponent. Or any other positive exponent close to 1. Will these results change, or do you expect? I mean, it seems to me that the theory should be very similar.
I guess, but because our way of analyze, so we heavily depend on the explicit form of the resultant kernel of square root of minus Laplacian. So I think you are right, but I'm not sure at this moment. But I think you are right. Yes.
Concerning the high energy behavior, so you don't expect the resolvent values to go down to 0.
No.
There is this Yamada result that for the Dirac operator, it doesn't go to 0, and morally it should be like the Dirac, right?
Yeah. So there might be a difficulty in that respect. Yes.
So what do you mean by the high energy behavior? To see if it is bounded at all, or?
We have no definitive idea.
Any other questions? Okay, so let's thank the speaker again.